This is section 3.5, angles of a polygon. We have objectives, two objectives, 4 and 5. Okay, here's a warm-up. Which one of these figures are polygons? There are more than one polygon, but some of them are not polygons. So think about it first and check the one that you think are not polygons here. Okay, and I tell you, so stop the video and I tell you which ones are polygon and which are not, and then we find out why later in this packet. Okay, all right, so the ones that are not polygons are this and this, not polygon. The rest are polygons. Okay, let's see. Okay, let's look at it and see what's wrong with this one and what's wrong with this one, and see if you're right later. Okay, think about it. Okay, so we are here, and this is the last section of this chapter. Here's objective 4. Recognize and name convex polygons and regular polygons. Okay, recognize and name. Okay, here are the rules for polygons, identifying polygons. Polygons, not polygons. What's wrong with this one? These are the definition of polygons. Polygons means many angles. Okay, each segment intersects exactly two other segments. Exactly two other segments, one at each endpoint. No two segments with a common endpoint are collinear. No two segments with a common endpoint are collinear. Okay, so this one, the problem is it's intersecting, not at the end but in the middle, right? This is no good. And this one is because it's a curve, and this one is not contained. And each segment intersects exactly two other segments at one at each endpoint. So this is a problem because it's not intersecting over here. Intersecting only once. And this one, no two segments with a common endpoint are collinear. No two segments is a common, so this is non-collinear. And this one, the problem is there's a curve here. I wonder if there's a better example for the two. Okay, so I guess because this is a curve, it's not a segment, right? So that's the problem. This is not a segment, okay? And this is not intersecting at each point. Okay, convex and non-convex. In this textbook, use the word non-convex. Other textbook call it concave. That's convex, that's concave. Okay, that's concave or non-convex. These are convex. So if you go back to the warm-up, that's convex, concave, concave, concave. You see, the concave means if you go from the two segments, there is a part that goes inside. Convex, if you connect the two segments anywhere, there is no side that goes inside. That's the difference. Okay, and we refer to a polygon in this textbook, we will mean a convex polygons. So concave we don't deal with in this textbook. Okay, when we say polygon, we are talking about convex polygons, not the non-concave or convex or concave. Okay, here's the name of the polygons. Polygons are classified according to the number of sides they have. Listed below are some of the special names of the polygons you will see in this book. So 3 is a triangle, 4 is a quadrilateral, 5 is a pentagon, 6 is a hexagon, 8 is octagon, 10 is decagon. The 7 they skipped, but because we don't use 7 much. And then n is n-gon. The 12 is called dodecagon. Okay, that's pretty much you all need to know. The angles is the simplest, triangle is the simplest polygon. The terms that we apply to triangles, such as convex and exterior angles, also apply to other polygons. Vertex and exterior angles also apply to other polygons. Okay, so let's say here is hexagon, right? Hexagon. These are vertices of a hexagon, and for example, that's one exterior angle of a hexagon. How many exterior angles does hexagon have? Yeah, 12. 2 at each vertices, right? 1, 2, 1, 2, and so forth. There are 12. Referring to a polygon and diagonal of a polygon. When referring to a polygon, we list the consecutive vertices in order. You remember you have to go in the order, like a square. You don't skip like this. Okay, you go in the order. Either you go counterclockwise or clockwise, as long as it's in the order. Pentagon ABCDE and pentagon BEADC are two of the many correct names for the polygons shown at the below. ABCDE or BAEDC. They are both correct way of naming this pentagon. A segment joining two non-consecutive vertices is called a diagonal of the polygon. The diagonals of the pentagon at the right are indicated by dashes. So these are diagonals. Okay, how many does it have? 1, 2, 3, 4, 5, 6. 6 diagonals. Okay, pentagon, 5 sides, there's 6 diagonals. Here is objective 5. Objective 5 is find the measure of interior angles and exterior angles of convex polygons. Okay, so how do we find the measure of interior angles, the sum of the measure of the interior angles? Okay, to find the sum of the measure of the angles of a polygon, draw all diagonals from just one vertex of the polygon to divide the polygon into triangles. So the quadrilateral can have only 2 triangles, because even if I did this, that's also 2 triangles, right? You just from one vertices, all the diagonal from one vertices, you do it from here or here. From here you make this triangle and this triangle. From here you make this triangle and this triangle. No matter how you do it, there are only 2 ways that you can cut it. This is 1, 2, 3, 4, 5 pentagon. So from this vertex you can draw this line and you can draw this line. You make 3 triangles. This is a hexagon, and from this vertices you can do here, here, or here, non-consecutive vertices. So 1, 2, 3, 4. You have 4 triangles. How does that help to get the sum of the measure of the angles of a polygon? Think about this. What do you think? How does this help is that because we know that no matter what kind of shape it is, the triangle, the angle sum is 180. We did that in 3-4, the section 3-4. So if this is 180, this angle plus this angle plus this angle is 180. And this angle plus this angle plus this angle is 180. What is the angle sum of a quadrilateral? Yeah, 360. The same thing here. This plus this plus this is 180. This plus this plus this is 180. And this plus this plus this is 180. So the triangle sum of a pentagon have to be 3 times 180, which is 540. And so forth. So this should be 1, 2, 3, 4. 4 triangles, 4 times 180 equals 720. So if you have an n-gon, what do you think the triangle angle sum is? Think about it now. Stop the video, and how would you express it? The total angles inside of the n-gon in terms of n. N-gon means there are n sides. So for hexagon, n equals 6. For pentagon, n equals 5. For quadrilateral, n equals 4. Okay, so if you were to express these numbers in terms of n, what would you get? Stop the video and come back, because I'm going to show the answer next page. All right, theorem 313. The sum of the measures of the angles of a convex polygon with n sides is n minus 2 times 180. Why is it n minus 2? Because for this one, n equals 4, right? 1, 2, 3, 4. And then you have two triangles, n minus 2 is 2. This one had 5 sides, 5n, 1, 2, 3, 4, 5. 5 minus 2, 3 triangles. Same thing here. This is a hexagon, so 6 sides. 6 is the n minus 2 is 4. There are 4 triangles. Okay? So that's why for the polygon, the internal angle sum is this. N minus 2 times 180. Theorem 314. The sum of the measure of the exterior angles of any convex polygon, one angle at each vertex, is 360. No matter how many sides there are, it's always 360. Why? Does the theorem 314 make sense to you? I'm sure you're all saying, no, it doesn't make any sense. Yeah. All right, so let's look at a hexagon. And maybe, I don't know, dodecagon. I don't know if I can draw this. I don't think I can. Something like that. Anyway, it's a polygon with a lot of sides, which get very close to a circle. All right, so let's just draw a circle and pretend that's like a 20 polygon or something. It gets very close to a circle. Okay, this is many sides. Okay, so if you are to consider the sum of the exterior angle, what would you do? So here's the exterior angle, one at each side of hexagon. Okay, so you have, here's one exterior angle, here's another one, here's another one, here's another one, here's the one. There are 6, because one at each vertex, so there are 6, right? And we are trying to find out what the sum of these numbers are. And this theorem is saying that no matter how many sides there are, so this one have tons of sizes. Okay, tons of sizes, tons of exterior angles. Tons of exterior angles. Okay, and then if you add all these little angles, if you add all the exterior angles of, I don't know how many, let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 20, 12, 13, 14, 15 gone. This one's a 15 gone. The sum of these 15 exterior angles is the same as the sum of this hexagon, the 6 exterior angles, and it's 360. Does that make sense to you? You'd think that this should be bigger, right? But each one of them is getting smaller, right? Because angle sum of a polygon is getting bigger as n gets bigger. Each n that gets bigger, the angle sum goes up by 180, right? So then exterior angles become smaller would make sense. But then why wouldn't this be smaller if this is 360? Shouldn't it be less? So here's a way to look at it. We are trying to get the sum of these angles, right? But we don't know that. However, you know the sum of these 6 straight lines, do we? This straight line is 180. This straight line is 180. This straight line is 180. This straight line is 180, and so forth. So for the hexagon, there is 180 times n of these angles, right? And we are trying to get the exterior angle sum. So if you could subtract the interior angle of the hexagon, so just these, from this number, we would get the exterior angle, don't we? Right? So you subtract from this the sum of the interior angle. Okay? So this is the 6 straight lines minus the sum of the interior angles should give you the sum of the exterior angles. Does that make sense? So for this one, the 15 one should be 180 times n minus n, I'm sorry, no n, we said 15. 118 times 15, and 15 minus 2, because there are 13 triangles you can make with this, plus 180, and you should get the angle sum of the exterior. For the hexagon, should be 180 times 6 minus 6 minus 2 times 180 should give you that. Okay, but just to instead of doing all this calculation, just do with n, because then if this is correct, then everything is correct. So that's 180n minus, you distribute 180, 180n minus 360, right? And now you have to distribute the negative. 180n minus 180n plus 360. Allah. This cancels, what's left is 360. And that's why it's always 360. Okay? Alright, so here is the practice, and we are done. So here's a couple practice and homework, and you're done. A polygon has 32 sides. Find the sum of the measure of the interior angles and sum of the measure of the exterior angles, one angle at each vertex. Okay. So let's just do this one, and you do this one for homework. Okay. This is video. Okay. All right. So A, n equals 32. Right? 32 sides. So 32 minus 2 times 180 should give you interior sum. So that means 30 times 180. And what would that be? 5400? That's a lot of angles. The angle sum over the 32nd gone is 5,400 degrees. That's very close to the circle. And B, the sum of the exterior angles. Do we need to calculate anything? Doesn't matter what the n is, it's always 360. Okay. All right, so you do 8 and regular polygons. Oh, we are not done. Sorry. There's regular polygon practice, and then we are done. We have 2 more pages. All right. Regular polygons are those polygons that have the same size and the same angles, or all sides and all angles. So that's a hexagon that is nothing. This is equiangular hexagon. So all the 6 angles are 120, but this side is longer than the other 4, right? And this one is equilateral hexagon. All the sides are the same length, but the angles are different. These are not regular polygons. These are just hexagons. This is a regular hexagon. Okay, so regular polygon means the angles and the sides are all the same. So a regular polygon has 12 sides. Find the measure of each interior angles. So how do we do this? First, we find the interior sum. So n is 12, so 12 minus 2 times 180 equal 10 times 180 is 1800 degrees, right? Now, how do we find each interior angles, meaning one of them? But they are all the same angles, right? So then we just divide by the number of sides. So 1800 divided by 12 equal 150. So for the dodecagon, each side is 150 degrees. Okay. So just think about it. If let's just say this is the one of the interior angles of dodecagon, that's 120, right? So what's exterior angle. That's a straight line, that's 120, so it's gotta be 60, right? 60 degrees the exterior angle. This is interior angle. And how many of these sides exterior angles does it have? It's a dodecagon, so it's 12. So 60 degree times 120 is not, I'm sorry, 6 degree times 12. There are 12 sides, 12 exterior angles. And that is, you get 360. Okay? 60 degree times 12. No, I'm sorry, it was 150. Sorry. I knew something was wrong. It's 150, so this is 30. This is exterior angle. Each of them is 30. So 12 of 30 is 360. Okay? All right. So now that you know how to do this, you can do this. Number of side, each measure of exterior angles, each measure of interior angles. Do this homework, and we are done.